So now I'll talk a little bit more specifically about the Nanocellulose project. And this is a cool one because it builds on that. And again, this is a specific strength at Virginia Tech is nanocellulose. And it was a great opportunity for interthrust collaboration. I'm also involved with the water sustainability thrust, many of you know. So this was all about sustainability. And so nanocellulose, we hope, it's natural, it comes from trees, so maybe it's non-toxic and it's a green super material. But of course, that's something we should probably investigate and confirm before we market it as such. These are some of its wonderful properties. It's strong, it's lightweight, it's renewable. Is it biodegradable? That's something we're trying to find out. And it's being used in all sorts of applications, including drug delivery. And we're starting to have some full-scale plants go online producing nanocellulose. And the production itself, even though it starts with trees, right, wood material, it is a pretty intense chemical extraction process. And this is Dr. Renneker's group has been working on just the isolation method for nanocellulose. And so we got talking and working on grant proposals and thinking about, well, you know, is it really biodegradable, right? I mean, we know cellulose is biodegradable, but it is hard to biodegrade. It requires this really complex subunit in the cell called a cellulosome. And, you know, nanomaterials, as we all know in this group, they're distinct from their bulk counterparts. So, you know, it is important to verify that it really is biodegradable. And then we're also interested in toxicity. So do the cells exhibit a toxic response? And so we've gotten started doing these suites of experiments in terms of biodegradation and toxicity, and using model cultures. One's representative of a wastewater treatment plant, and another's representative of a wetland, like where you might discharge water. Now, if nanocellulose itself is non-toxic, that's great, but we have to think about the functional groups, right? Because it's typically going to be functionalized with something. And so we picked representative subset of neutral, positively, and negatively charged subgroups to see what happens. And one possibility here is that it might become a test material to isolate the effect of that functional group from the effect of the nanomaterial itself. So we've got these cultures going, and we're going to expose them to the nanocellulose with different functional groups. We'll do metagenomic characterization. And then, of course, we'll characterize the nanocellulose itself and get evidence of biodegradation and what's actually happening to it. And I think quite a few highlights. I mean, for this being a relatively new area, we've got 2 publications. So the first, working with Mike and his former postdoc, Deborah, looking at this issue of nano-antibiotic resistance. So we got a review paper out there to get that idea out there, and then that's laying the framework for future studies. And then we did get one paper out looking at nanosilver in wastewater treatment plants, and Pete was a partner in that, and also John Novak. And Renneker's group got a new HPLC, which has been key in being able to analyze the biodegradation. We have, I already mentioned the EPA project was funded, but this NSF one was really born out of ICTAS, and really the interthrust collaboration was really attractive to getting this funded. So I think that's my 2 talks.